We are Team Bumblebee. I'm Chan Wai, a 4th-year mechanical engineering student and the current team lead.
My name is Samuel, a 4th-year mechanical engineering undergraduate at NUS.
Hi, I'm Dimitri, a 3rd-year computer engineering undergraduate from NUS.
My name is Alex, a current 4th-year computer science undergraduate at NUS.
This year, Team Bumblebee has decided to deploy a single vehicle to complete all of the competition tasks. By devoting all of the development time into a single vehicle, our engineers were able to do a deep dive, making huge improvements to the mechanical, electrical, and software subsystems, culminating in the brand new BBAUV 4.0, which has all the capability of the previous generation BBAUV 3.5, while being much faster, lighter, and much more maneuverable. Let's see what the team has been up to this past year.
The mechanical team has focused its time on improving the robustness and reliability of the vehicle. Our new shell greatly improves its resistance to impact, allowing us to approach tasks more aggressively. Expanding the frame into its new orthogonal configuration allows us to fit more actuators into the same space. We have also switched over to 100% electronic actuators, ensuring 100% reliability when attempting new tasks.
The electrical sub-team has focused on improving the performance of the vehicle as well as the ease of testing. We have upgraded our ESCs to the VESC 4.12, which brings our thruster response time down from 300 milliseconds to 5 milliseconds, giving us greater control over the AUV. This vastly improves the PID controls on the system. To aid in debugging hardware, our backplane system allows us to easily remove PCBs. To maximize our time spent testing, we have hot swappable batteries, which allows the AUV to be constantly powered even during battery changes.
This year, the software team has focused its upgrades on 3 major areas: the mission planner, the machine learning pipeline, and the control subsystem. After a year of using our behavior tree-based mission planner, we have identified several flaws and have simplified the implementation to allow for the easier editing of behavior trees. Next, for machine learning pipeline, we have moved to Python 3 and TensorRT for greater performance and increased reliability. Lastly, but perhaps most importantly, our control system has been upgraded to make use of control law partitioning. This has greatly improved the performance of large setpoint goals by avoiding controller saturation. The use of positional and velocity tracking allows us to move the AUV with much greater precision than before. For the first task, the strategy is simple. Since we know both the relative position and the orientation of the gate from the dock, we can simply make use of a highly accurate DVL and IMU to localize the AUV and move through to the correct side of the gate. Along the way, small corrections are made using machine learning as well.
With our new protective shell and frame, we can be sure that the BBAUV 4.0 can sustain impact without affecting any of its mission-critical components. This gave us the confidence to use it to perform the buoy task, which was previously assigned to the BBAUV 3.5.
Using our vision pipeline, we are able to combine both sonar images and machine learning object detections to localize the buoys with pinpoint accuracy. Completing the task then simply involves identifying the correct buoy using machine learning and navigating to its reported location given to us by our vision pipeline, only needing to make small adjustments along the way.
Our new servo-actuated ball dropper holds 2 balls and drops them on command. Reloading is quick and easy with our magnetic loading system. In our testing, the system has been able to place the ball in the bins reliably 8 out of 10 times. Our newly improved grabber uses only a single stepper motor and a couple of bevel gears. The reduced weight allows for greater mobility without compromising the capabilities of the gripper.
Unlike the make the grade task, this bottom-facing task makes exclusive use of machine learning, since we are unable to use the forward-facing sonar. Using our highly accurate machine learning models, we are able to track the centroids of the 2 images and the lid so that we can align the AUV to be able to pick up the lid using our grabber. After picking up the lid, this alignment process is repeated so that the AUV can drop the marker into the bin.
Our new spring-loaded torpedo launcher can hold 2 3D printed nylon torpedoes and fire them over 4 meters in air and up to a meter when submerged. With minimal shot deviation, the software team can attempt this task from near or far.
The vehicle will be guided to the obstacle by the use of the acoustic subsystem. We obtain azimuth as well as elevation of the pinger through the use of the music algorithm. The signal is identified using a dynamic thresholding method based on the short time Fourier transform. This reduces the number of false positive readings encountered. To decrease latency within the subsystem, we have implemented a field-programmable gate array which allows signals from all 4 hydrophones to be processed in parallel.
Just like the make the grade task, we make use of our vision pipeline to accurately localize the torpedo boards. However, for this task, the heading of the AUV is critically important, and so we also check the torpedo board's 6D pose using homography and 2 views zero vision. For the final alignment, machine learning is used so that the AUV can approach the torpedo openings and fire the torpedo.
With recent updates to the orientations of the bottles, the team is working to adapt the grabber such that it can grab the bottle in either the vertical or horizontal position.
Similar to survive the shootout, elevation and azimuth information of the pinger is extracted using the acoustic subsystem. With this information, the AUV then navigates towards the cache or smash task.
Like with the collection task, we plan to make use of our robust machine learning object detections, but also augment them with traditional computer vision techniques to accurately get the angle of the objects, so that we can align our AUV and the grabber with the objects. Since our grabber is better at picking up horizontal bottles, we plan to knock over the vertical bottles such that we maximize the chances of completing this task. Bringing everything together is our behavior tree-based mission planner. Behavior trees offer many advantages over traditional finite state machines, allowing us to easily configure robot behaviors by simply repositioning nodes in the behavior tree, without having to worry about transitions between states. This allows us to come up with an extremely robust mission plan that considers many failure scenarios.
Through this year of research and development, Team Bumblebee is proud to present BBAV 4.0, the best version of the vehicle that the team has put forth yet. Look out for us in this year's Robosub 2022 to see the vehicle in action. See you there!